right? It's sort of like I could give you a sequence of pseudo-holomorphic curves where after a finite set, your domain of your curves is empty. I mean, that's kind of a stupid sequence, but I would still say that for purposes in some sense. Yes, if it's the case that you want to make sure that you end up with a limit curve which is not nothing, then you want to demand it to be the case, for instance, that your curves always intersect some compact region on the interior. My plan on this was to discuss targetable Grove effects a bit more tomorrow for those interested. Yeah, so there are some sort of technical details. But the idea basically is you sort of say, look, I've got a bunch of curves in this region right here. They have area bounds and genus bounds. Then essentially a subsequence converges modulo sort of trimming near the boundary. And if you want to be left with something interesting, they better intersect deep interior. Any other questions?
In some sense, it's an interior regularity state, but that's on the trace number wave and the particle which lies in some tube.
So, yes, sorry.
So your answer is like domain integration from a stream integration.
Maybe. So the way I think of it is, so my attitude is that pseudo-holomorphic curves really just want to be essentially surfaces. You should think of them as submanifolds, not as maps. From the map perspective, when you prove Gromov compactness, you sort of say, okay, you can have bubbling, you do rescaling, and then you sort of say, what happens if I have a sequence of curves with boundary, and then the gradient blows up as you run to the boundary? Well, you sort of say, I still have compactness if I just sort of trim away a neighborhood of the boundary. But the neighborhood of the boundary there is in the domain of your curve. And the problem is the neighborhood of the boundary in your domain might sort of, the image of that might be all over the place. And so the key idea that I sort of brought to this was that you can trim essentially in the neighborhood of the target boundary, and then a subsequence will converge in that case. Right? Okay.
So I can feel the seeds, but now feel you're done.
Now we're getting started. Yeah. So the idea here is, so now with this attitude, oh, it must be done, or close to done, is exactly this idea of, oh, this, I now have a limit in some sense. I've found a curve, right? It has finite omega energy, finite genus. It sort of runs up to the end, runs up to sort of the positive end. It should be the case that it's just going to limit to some closed invariant subset, and we're done. Okay, except it's harder than that. Why? Well, there's a couple of reasons. Remember, we don't have energy bounds. And a lot of properties that are nice, that the pseudo-holomorphic curves have, extend from having energy bounds. So, how bad could it be? Oh, if it were only 20 epsilon, Selma would be happy. It was, let's see, what was it? I think it was 2 to the minus 24, I think. Let epsilon be less than 2 to the minus 24. There's a lot of epsilon over 2 arguments. Yeah, I was not efficient with mine, but it's already seemed pedantic enough. Right, so there's this idea of, well, how bad could it be? So let's start asking questions like, okay, we have no energy bound as we run up the end, but we do have this, omega energy is finite, so what could be happening? Well, yes, it's proper. It's proper. That's sort of, yeah, that's true. That plays a role. So the first main thing to kind of visualize what could happen is just imagine you have an orbit cylinder, right? And in a nice contact case, and you've got sort of an approximate, that curve which is sort of approximating this orbit cylinder. But it doesn't approximate in sort of a degree 1 sense. Suppose it's very close to being like a branch double cover. If the branch double cover of an orbit cylinder, then it looks like a pair of pants. But maybe it has one its boundary components connected on the bottom and then disconnected at the top. That can happen. And you can do that with 0, omega energy or d lambda energy. So if you can do that, if you can do it in this case, you can sort of wiggle it and imagine that could happen, and then you end up with something, well, maybe it's the case that I start down and have one positive end, but then maybe it kind of splits off into sort of 2 things, but then maybe each one of these then splits off into 2. Right? Oh, but then maybe those split off into more. And more. All right. So then the next thing is to say, well, so that's one issue. That's sort of.
Where things start bulging off and stuff like whatever.
Yeah, and you sort of say, well, I mean, but could this really happen? But remember, how does the area blow up? This sort of sheeting effect, right? And so if you have this sort of sheeting effect, you can imagine just sort of you put in a little sort of top volume switcher here, and then suddenly you've done something like that, and then you can do something over again. So this is one problem. So if you have something like that, where the case you say, oh god, that means my domain is a Riemann surface minus some infinite collection of points. And that seems bad until I tell you, oh, but it could be worse than that. It could be worse because instead of this being a sphere minus some collection of points, right, some discrete set of points or some countable collection of points, it might actually be a disk minus some collection of closed disks. Your domain of this thing might be a disk minus open disks. And it might be infinitely many. I can't rule that out at this point. Your domain is not a punctured Riemann surface. Right, it's always the case that as you run out to the end, your limit, you want to be able to sort of, reparameterize and sort of think, I've got some sort of half cylinder here, for instance, and somebody would say no.
Also, don't forget that something which looks like a plane could be, in the context I'm saying, uniformized by one dimension sphere, but it could be uniformized by both bits. We don't know.
And so one of the things that's sort of interesting about this is something that this idea I've used a lot, it's been very fruitful for me, is always this idea of let's run some terrible notion of compactness, something that's just awful, and everyone say, well, how is that ever going to be useful? Construct a limit, and then make use of understanding, and then use that understanding of how you got to that limit to sort of back up in the sequence and then extract additional properties. So for instance, in this case here, you might say, well, maybe in some sense we have a whole bunch of positive ends developing sort of arbitrarily many. But then the idea is to say, well, wait a second, what if you backed up in the sequence? So you back up in the sequence, and now this is now sort of capped off by some curve that sort of runs up into sort of the top end of sort of CP2. But at some energy level, at some fixed energy level here, you have a whole bunch of these loops. So maybe arbitrarily many. But the thing is that it's also the case that sort of above this region now these loops can't come back to each other because then you have genus and our curve started with 0 genus. And if they stay disconnected, well then they either have to run into the very top or they have to be capped off by some sort of some disk like this. But then when you can prove this is sort of the second thing that we prove in the paper is that each one of these, if you have capping disks like this, each one contains the threshold amount of omega energy. If you have a threshold amount of omega energy on each one, then you have to have only finite omega. And this works whether or not they're sort of capping in sort of the R varying region, or if they run into the actual sort of coordinates piece, they also have to capture sort of a threshold amount of energy there as well. That's basic quantiticity, and so that's ruled out as well. And so as a consequence of this, in some sense, you now have an upward bounded number of positive ends that you have. Well, no. You have to argue that these sort of caps exist. The only thing that you're sort of, well, okay, so the only thing that you're worried about, right?
If you have a cap, so it makes it has
Yes, that's true.
and then it backs off. The concentration discards.
Yeah.
Yes, but if you work in the stretching construction with upper final number of energy, this number of ends has to pass.
Yeah. Do you still want to know why is it the case that we have an energy threshold? Don't make energy threshold on these caps or no? No, I didn't prove that. I didn't prove the threshold yet. It is a threshold. I have an area bound. Yeah, go above. Exactly. Yeah. So each one. So it turns out that the argument that says that sort of the area bound near the minimum is bounded, right? The area, the full area near the minimum is bounded. There's really that's not the sort of thing. In this case, there's no up and down anymore. Everything is every which way, which was the same argument works if you have a maximum. That gives you an area bound, an upper bound on area. But now what that means is that every one of these caps essentially has an upper bound on area, right? And so you sort of say, well, basically what you argue about is that a compactness argument. And you sort of say, well, is it the case that you can have a sequence of caps like this, zero genus bounded area, which have arbitrarily small omega energy, and you can see that, well, if you did, you have to converge to something which was actually sort of a patch of an orbit cylinder, and that would violate having an absolute mass. That's essentially the argument, right, for the omega energy. And so that rules out this possibility. So now that's sort of nice. You sort of say, oh, okay, I have some finite number of ends. That's great. This is sort of wonderful.
So for me, I have to worry about on the number of these tentacles that are ending up.
Yeah. And that's yes.
Coming from the stretch.
Coming from a stretching construction. So I'm more or less
Principally, you could find things which just have more ends.
yes. So it depends. Those I think will never arise from a stretching construction. Abstractly, such things should possibly exist. So because the idea is to back up in the sequence, right, and sort of say like, okay, well, if we back up in the sequence, then these weird ends haven't sort of run out to infinity. We're backing up, and so now the image of our pseudo-Halmar approximating pseudo-Halmar curve is living in some sort of stretched CP2. We haven't dropped all the way down to sort of nice infinity yet.
That's what you want to try to see.
Yeah.
So when you say stretching construction,
so at this point, let me so if you think about sort of what properties does sort of our limit curve have here, because the idea is to say what properties does our limit curve have, and then use that to define a new class of curve, and you might say a Farrell curve, say for instance, right? And I think if the first attempt is to say something like, well, sort of, let's say, I should really say, the zero is that U needs to be proper. That's the only way any of these curves sort of make sense. You also might want it to be the case that the omega energy is finite, and you would want it to be the case that you have, that the genus is also finite, and you might sort of say maybe this is enough. And what I'm saying is that I can't do interesting analysis with just these conditions. It turns out that to actually do, like to get, for instance, that area bound that you were mentioning, that connected local area bound, in order to get that, I need to have finitely many positive ends. And so we generalize this notion of puncture. And we want that to be finite as well. You have to throw in that condition. If I don't, then it screws up later actual metric analysis. The number of ends, yeah, you have sort of ruled out. The thing that sort of we ruled out the infinite case with these caps. Yeah. But you could allow to have sort of negative ends as well. That's now sort of okay. But you have sort of bound to the number of negative ends as well.
Negative side and positive side, but now here there's no both sides.
So this is. So this very nearly is the definition of a Farrell curve. A curve which satisfies this collection of properties. I'd say that there's one more in this case, though. If you want to add in mark points, then the number of mark points has to be finite. If you want to add in nodal points, the number of nodal points has to be finite, and the number of connected components has to be finite. So some basic topological properties. Number of mark points plus number of nodal points plus the number of connected components of your domain has to be upward bounded, and then this is the correct definition of a Farrell curve. Right?
As a sequence, you want each of those to be
Yeah, you want to bound on all of these. You want to bound on all of these. Yeah, you want to bound on all of those if you want to proceed. You want to try and run some sort of compactness again. And in that case, you could then extract sort of, let's see, even in that case, it's possible that you have no dice on an SMT type compactness. And that's only though because you have to allow curves which have both positive and negative ends. And then in this case here, it could be the case that sort of everywhere the energy kind of blows up to infinity. And you can't extract something. You can't extract a curve with minimum or maximum, say for instance. So it gets hairier in that case, but it's already.
you're saying that
Genus and punctures. No, there's no way for me to, as far as I know, if your curves come from a stretching construction, then the number of punctures that you get is bounded. If you're just talking about sort of walking down the street and someone hands one of these to you, it seems to me that, it could be sort of infinite. And so I'm out of time. I want to say sort of just a couple things. And that is, at this point, here, you say, okay, I have a positive number of ends, things still should be good, right? It still should be the case that, like, oh, now I only have a finite number of positive ends, maybe it's sort of not so bad. There's all sorts of very strange things that kind of screw up your analysis. So, for instance, there's no reason why you can't have, like, in some sense, you can't have, like, this sort of appear over and over and over again. Right? Or worse, like, why can't you have something which sort of, as you sort of point out at the end, sort of you have these little dips and sort of stupid little things that sort of happen.
Jangan bayar dulu. Itu kalau di bawah berarti gimana ya? Karena kamu kan bukan cuma bayar tapi kamu bayar aja cuma bisa kasih dia. Mau ada di mana? Kamu bayar bayar dulu. Saya kamu jangan bayar dulu ya?
Juga hilang tadi.
Kalau aktif kalau connecting loh. Ada di sini kok.
Ya tadi kita
Halo. 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 Ada di mana kamu samperin?
Jadi gitu Pak.
Lantai berapa nih?
Apa sih? Iya sih.
di lantai yang
Halo. Mereka mau bayar kalau mereka kena karena aku bilang sama kamu mereka kamu kan harus dia. Iya, makanya dia tadi kan aku bilang kamu samperin kasihan mereka nggak ngerti.
Oh.
Thank you.